Hello, everyone. I'm Deepak. I'm an assistant professor at the University of Illinois, Urbana-Champaign, and today I'll be presenting this topic preview on wireless and mobile networks, session 1. Honestly, this is a very exciting session, and it should be called New Frontiers in Wireless and Mobile Networks. So let me start by talking about some of the new frontiers that have emerged in this domain of wireless networking research. First, let's talk about personal devices. Till about 1 decade ago, smartphones used to be the primary personal device that we have. But now we have so many other devices around us. Think about smartwatches that monitor our health, track our activity, even ping us when we are feeling too lazy and ask us to go for a walk. They can perform many more applications as well. Similarly, we have augmented reality headsets or virtual reality headsets that transport us to a completely new world. They have many applications in gaming, entertainment, and even in productivity and in the industry, for example, digital health or remote presence. And finally, we have smart earables devices that interact with our ears, like my headphones or small earbuds or truly wireless earbuds that people are used to using. And again, for these devices, you can interact with them, you can talk to them wirelessly. And each of these devices represent a big segment in the industry. Just AirPods alone generated $23 billion of revenue in 2020. So let's zoom out a little bit and talk about our home. Our homes are increasingly getting smarter, and again, because of wireless networks that connect multiple smart devices in our homes. For example, we have smart robots like the Roomba that goes around and vacuum the house. We have smart light bulbs, thermostats, smart cameras, and our traditional devices like laptops, smartphones, iPads, so on and so forth. And all of these devices are connected wirelessly and interact with each other. And these devices keep increasing in number. In fact, it's estimated that we'll have 25 billion of these devices by 2025. Next, let's zoom out a bit more and talk about networks at the scale of a city. Cities will increasingly deploy a large network of sensors to monitor and regulate traffic in real time. Networks that can reduce traffic, reduce congestion, and as a result, reduce pollution in busy cities like London and Beijing. In addition, we'll soon have autonomous vehicles that need continuous connectivity and help from smart infrastructure that's being deployed in these cities. This is becoming even more crucial when traditional modalities of autonomous vehicles like cameras and LiDARs have well-known failure modes, like they can't see through fog and smog. They're increasingly rely on smart infrastructure assistance and real-time low latency networking. And finally, let's zoom out even more and talk about planet-scale networking that's being envisioned through low Earth orbit satellites. Many companies are launching networks of hundreds of satellites for multiple applications. And the reason that this is possible today is because the cost of launching these satellites has decreased significantly. So each satellite that used to cost tens of millions of dollars can be built for hundreds of thousands of dollars today. And launching these satellites is also relatively cheap because you can pack many of them into a single rocket and launch them into space through rideshare agreements. And think of this like Uber Pool for space that reduces the cost of launching satellites. And these satellites are mainly for two different applications. One is satellite connectivity that is providing internet to areas and locations that did not have internet before, such as rural areas and farms and forests, and also for Earth observation, where they take pictures of the Earth and use for many different applications like precision agriculture. An example that I saw recently was this image that New York Times used to analyze the movement of crowds and aeroplanes in Kabul after the recent conflict between Taliban and the Afghan government. So we have these new frontiers operating at multiple scales. We have personal devices operating at the human scale, smart Internet of Things connectivity at the home scale, city scale networks of sensors, autonomous drivers, and humans, and finally, planet scale networking through satellites. This is a massive spread. And the exciting bit about this session is that it's going to talk about all of them. First of all, there'll be a paper that talks about personal devices. So let's think about what are the important research problems these days in the space of personal devices. Well, the first thing is we want these devices to be personalized to ourselves. If I wear a smartwatch, I needed to know my schedule. I needed to figure out when I typically walk and encourage me to walk at that time. I needed to interrupt me once in a while if I'm sitting for too long. And also probably to figure out my sleep schedule and see if I'm sleeping healthy, sleeping at the same time every day, so on and so forth. So this requires very fine-grained personalization. At the same time, we want these devices to be low power. For example, I don't want to be charging my headphones and my earphones and my smartwatch every day. Like as the number of devices increase, the pain of recharging these devices is also significant. So ideally, we want these devices to operate at a really low power so that I don't have to keep charging them again and again. And finally, even though I want these devices to be personalized to myself, I want to ensure that the data that these devices collect is private and secure and does not really get leaked that easily. So the paper that we'll hear about today focuses on the personalization aspect. And fundamentally, the question it asks is, when I wear my headphones, why do I hear sound differently than when a real person is talking to me? So for example, if I'm talking to someone outside, it's a very different experience than when a sound comes through my ears. And it's almost never happened to me that, or it happens rarely to me that I would be confused that something that's being playing in my headphone is actually coming out from the real world. So why is real world sound so different from the sound that propagates through these devices? And this paper is actually very interesting because it reveals that the reason that the sound in the real world feels so different is because of our head. So as the sound waves travel, they get reflected and diffracted around our head. They experience all of these weird effects that this paper will talk about that cause the sound to feel a little bit different. And this paper defines this mathematically as this head-related transfer function. And this paper actually goes a step further and computes the unique head-related transfer function because all of our heads are different. So we'll have different transfer functions for the sound that's coming out of the real world. And it computes this unique head-related transfer function for each individual. And it has so many applications like virtual reality, gaming, entertainment, and navigation assistance, so on and so forth. Okay, so the next paper focuses on smart homes and the home scale. So what are the problems that exist at the scale of homes? Well, first and foremost, scaling is an issue. We have tens to hundreds of devices in our homes, and all of them need to be connected. And what makes this problem more challenging is heterogeneity. That all of these devices are different. They use different protocols, they have different app interfaces, they have different power requirements, they're located in different locations. For example, some of them are located on the ceiling, some of them are close to the wall, in a weird corner, or in my pocket, for example. And finally, we want to provide connectivity and coverage throughout the home. So I don't know if you've had this experience when you go home, buy a new router, set it up, and you walk around with your smartphone. And of course, there will be some locations where you don't get good connectivity. And you have to try to figure out how to move this router around so that at least on your study table and your couch, you get connectivity. You probably don't need it everywhere. It's a pain. But imagine what happens when we have these devices not just distributed in a 2D space around me, but also in a 3D space. So there are devices on the ceiling and on the floor and embedded in my walls and in some corners. This problem of connectivity and coverage becomes so much more challenging. And that's exactly what this paper tries to solve. So this paper is called LAVA, Fine-Grained 3D Indoor Wireless Coverage for IoT Devices. And at the fundamental level, it asks, what can the home do to extend the coverage of wireless links? So you go ahead and put your Wi-Fi router wherever you want, and it will still be able to talk to all of your devices because your home itself is smart enough to relay these signals. And it does that through this thing called LAVA, which is a large array of vanilla amplifiers. And I'll not go into the details because I don't want to steal the punch of this paper. But the high-level idea is that you put a lot of amplifiers in the surrounding itself, you embed them in the home. And this grid of amplifiers can help strengthen your signal, can help your signal when it's kind of feeling weak. And more interestingly, this will work with all kinds of protocols like Zigbee, Wi-Fi, and it's not limited to just one protocol that you designed this grid for. There are several questions that this paper answers. For example, how would you control this grid of amplifiers? And what kind of performance improvement can you expect when you deploy this grid of amplifiers in your house? Okay, so now let's shift our attention to city-scale networks. And in city-scale networks, there are multiple research problems that people are focusing on today. And one of the more interesting ones is infrastructure assistance for autonomous vehicles. So, there has been a lot of investment in terms of real dollars in autonomous vehicle research and in developing autonomous vehicles. And yet there is something missing. And one of the problems is that autonomous vehicles typically rely on sensors that they have on them. For example, cameras or LiDARs, but these sensors are prone to failures. Like in smog and fog, you cannot use a camera to reliably see through these obstacles. And as a result, the accurate sensing of pedestrians and road signs has become a challenge. The other problem in this space is low latency connectivity because these cars are moving at relatively fast speeds. So you want to convey the information to them as fast as possible. And finally, you want ubiquitous coverage of networks in homes. Finally, you want ubiquitous coverage of networks in cities, not just for cars, but for people, for outdoor devices, sensors that are being deployed in these cities. So we have a paper today called Passive Smart Surface for Roadside-to Vehicle Communication. This paper has a very interesting idea for infrastructure assistance for self-driving cars. And the idea is that you can put a small tag on these stop signs and different kind of road signs that can communicate their existence and actually communicate information with autonomous cars. And what makes this even more interesting is that you don't even need to change the car hardware. The car can use its radar, which is millimeter wave based, and these tags can just reflect that radar signal and create small patterns in these reflections that will communicate bits of information. I'll encourage you to check this talk for details, but there are multiple interesting questions to ask. For example, how do you embed this information in radar reflections? And do these tags themselves need any power to operate, or can they be made really low power? And finally, let's talk about satellite networks. So in satellite networks, there are two levels of challenges. One is the scale. Previously, we used to have few satellites in space, and we would get small amounts of data from them. Now, these modern satellites are deployed in constellations of hundreds to thousands of satellites, and they generate hundreds of terabytes of data per day. How do you communicate this data between space and Earth? And the second challenge is specific to this new wave of low Earth orbit satellites. In the past, we had these traditional satellites which operated in geosynchronous orbits, which are kind of really high, like 20,000 or so kilometers above the Earth's surface. And because they're so high, they move relatively slowly with respect to the Earth. As you can see in this figure, a geostationary satellite is actually stationary with respect to an observer on Earth. But modern satellites operate much closer in low Earth orbits, about 500 kilometers above the surface of the Earth. And as a result, they move much faster with respect to Earth. So if you have a wireless device that's connected to the satellite, it has to deal with all of this mobility. So this paper, L2D2, low latency distributed downlink for LEO satellites, tries to solve this problem of data download, even though these satellites are moving at such fast speeds. So the fundamental question it asks is, how do you download terabytes of data from these satellites at low latency? And I'll not go into the details of the solution, but at high level, it proposes a new design for Earth infrastructure for downloading data from these constellations of low Earth orbit satellites at low latency and at high throughput. So here is the exciting session. These are the 4 papers that we'll talk about today, not necessarily in the same order that I discussed them. I took some liberty to go from the human scale to planet scale networks, but they're in a slightly different order. I hope you enjoy all of these papers today. Thank you so much.